Okay, let's dive deep into this stack of sources you've sent over.
Yeah, there's a lot here.
It's all about Nvidia's major push into humanoid robotics,
Yeah.
specifically Project Groot.
Right. Big focus for them.
And this deep dive, it's really tailored for you, the listener, who wants to get a handle on this, well, this super complex, fast-moving field.
Without getting totally lost in the weeds.
Exactly. So our mission today, pull out the most important nuggets, the why, the what, the how behind building these human-like robots.
And it's all straight from NVIDIA's experts based on these sources.
So what does this mean for you? Basically, getting informed quickly, thoroughly on something that sounds like pure sci-fi.
But is rapidly becoming reality. It's fascinating stuff.
What jumps out at you first from this material?
Just the sheer scale of the ambition. You know, this isn't just some lab experiment. It feels
Yeah.
like a response to some really fundamental global issues. And, well, a huge bet on a massive economic opportunity.
That comes through so clearly. The main driver, the big why. It starts with this pretty stark trend.
The job vacancies.
Yeah, a 4.2 times increase in job vacancies in advanced economies over just the last decade.
Wow.
And here's the kicker. Tons of those jobs need physical work.
Right. Hospitality, healthcare, construction.
Transportation, manufacturing.
Yeah.
Roles you just can't fill with an LLM no matter how smart it is.
Exactly. That physical gap is key. And the economic impact.
It's staggering, isn't it? The sources mention a $1.4 trillion annual gap.
Trillion with a T.
Yeah, that's like, what, 1.5% of the entire U.S. GDP?
Or, yeah, the whole GDP of Spain or Mexico, roughly.
Just lost value because there aren't enough people for the jobs?
That's the prize. That's the huge incentive to solve this physical labor problem.
Okay, a $1.4 trillion annual prize, that's
Yeah.
That's serious motivation.
Definitely.
And they also stress that the hardware is becoming way more feasible now. The cost, it's plummeted, right?
Massively. They compare it to NASA's Robonaut back in, 2001? That thing costs about $1.5 million. And that's 2001 money.
Right, not adjusted for inflation.
Exactly. But today, you're seeing capable humanoids around $40,000.
$40,000, that's like a car.
Pretty much in the ballpark of a new car. And the key thing is, they predict costs will fall way more as production scales up.
Makes sense. Less material than a car, too, probably.
Right, much less mass.
Okay, so you've got this huge unmet need, massive economic rise, cheaper hardware, but why humanoid? Why that shape? Why not, a robot dog or just an arm on wheels?
That's where the Brownfield project argument comes in. It's actually really smart.
Brownfield, like existing sites.
Exactly. Think about it. Our entire world, factories, hospitals, warehouses, construction sites, even our homes.
They're all built for us,
Yeah.
for humans.
Precisely. Designed for a two-legged shape with arms, hands, things that use human tools and navigate human-sized spaces.
So a humanoid robot could theoretically just walk in and start working.
Potentially, yeah. Using existing infrastructure, existing equipment, no need to rebuild everything from the ground up.
That saves a lot.
A huge amount. It makes it the most versatile body for a generalist robot that needs to operate in our world.
And they point out that the robots themselves are getting much more capable physically.
Oh yeah, the agility is improving rapidly. We're seeing some really dynamic human-like movements and examples.
Okay, and there's another angle too, right? The data angle.
Yes, the data argument. This is crucial. Because humanoids share similar physics with us, there's this potential to tap into the vast amount of human data out there.
Like what? Motion capture.
Motion capture libraries, yeah. Or just think about YouTube. Billions of hours of video showing people doing, well, everything.
So the robot could potentially learn by watching us.
If they can figure out how to extract the right information, yes, it could be a massive shortcut for overcoming that robotics data bottleneck.
Okay, that clicks. The why is strong. Labor shortages,
Yeah.
economic value, cheaper hardware, plus the humanoid form factor is just practical for our world and maybe even for learning.
Makes a compelling case.
So let's get into the what. What exactly is Project Groot at Nvidia? It sounds bigger than just one robot.
Oh, much bigger. Groot isn't a single product. It's positioned as their comprehensive strategy, their platform for building, well, what they're calling physical AI.
Physical AI. Okay.
It maps out the whole life cycle. You need to generate the data first.
Right, the training data.
Then you need to consume that data to train the models, build the intelligence. And finally, you have to deploy those models onto the actual robots so they can work autonomously out in the world.
Generate, consume, deploy.
Yeah.
Got it.
Yeah,
And they connect this directly back to their hardware, right? With 3 types of computers.
exactly. It's structured around these 3 defining computers. First up is the OVX.
Okay, OVX,
That's their simulation computer. This is where they generate all that synthetic data.
in virtual worlds.
Yep, using powerful tools like Isaac Lab, which is GPU accelerated, or even using teleoperation, like controlling a virtual robot with XR headsets.
So step one, create tons of virtual training data.
Right. Then you need to process all that data, build the AI brain. That's computer number 2, the DGX.
The training supercomputer.
That's the one, where they take these massive data sets and compress all that knowledge into foundation models.
And that's where the Groot N1 model fits in.
Precisely. The Groot N1 foundation model gets trained on the DGX.
The AI brain is built there.
Okay. Then, once it's trained, that brain needs to run on the robot, in real time, out in the world.
Needs to be efficient, low power.
Exactly. Which brings us to the third computer, the AGX, specifically their new Thor platform.
Thor.
Yeah. Designed as the edge compute device. Sits right on the robot, runs those complex AI models autonomously, enables the robot to perceive, think, act.
Okay, OVX for simulation and data gen, DGX for training the AI, and Thor for running the AI on the robot.
That's the framework, a very clear end-to-end strategy.
It really shows they're thinking about the whole pipeline.
Absolutely.
All right, now let's dig into the how. The research principles driving this day-to-day. They lay out 3 main ideas. First one, generalist.
Yeah, this one's really interesting. It's inspired by what we saw with LLMs, right? Like ChatGPT or Llama.
Oh, so?
Well, the idea is instead of building specialized models for every single robot task from scratch, you build one big, powerful generalist foundation model first. Train it on a huge variety of tasks, lots of different data.
Kind of universal starting point.
Exactly. This generalist model then acts as a flexible backbone. You can then adapt it or specialize it much more easily for specific jobs or environments.
You're not reinventing the wheel every time.
Right. They're careful to say it shouldn't be a jack of all trades, master of none, though.
Okay.
The goal is building this core competence, this foundation, that lets the robot keep learning and become really expert at whatever it's deployed to do.
Makes sense. Continuous learning. Second principle, dual system. They connect this to human thinking.
Yeah, the whole thinking fast and slow idea from Kahneman.
Oh. Yeah.
They envision 2 systems working together in the robot's control. System 1 is the fast part.
Like reflexes.
Exactly. Fast, unconscious, reactive control, handling things like balance, walking smoothly, reacting instantly to bumps or changes. This needs super high-frequency updates.
How high?
Hundreds, maybe even thousands of times per second, kilohertz range.
Wow. Okay, that's fast. And system 2?
System 2 is the slower, more deliberate part. Conscious reasoning, planning.
Thinking things through.
Right. Understanding complex instructions, figuring out a multi-step plan, dealing with the new situation it hasn't seen before. This runs at lower frequencies, maybe 1 to 30 times per second, 1 to 30 hertz.
Much slower. So the big challenge is getting these 2 to work together smoothly.
That's the huge research challenge, yeah. Integrating fast reflexes and slow strategic thinking into one coherent, reliable system.
Tricky. Okay, and the third principle tackles that data problem we talked about, the data pyramid.
Right, because like you said, there's no internet of human-controlled data just lying around like there is for text or images.
Yeah, the bottleneck.
So their approach is pragmatic, use multiple data sources, they visualize it as a pyramid.
Okay, what's at the top?
Real-world data, usually high-quality, direct experience, often gathered via teleoperation where a human controls the robot.
But it's scarce and expensive to get.
Exactly. Small volume, high cost, that's the peak. Below that, there's web data.
Like the YouTube videos.
Yeah. Billions of hours showing humans doing things. They call this the fossil fuel of AI for robotics.
Ah, I like that. Fossil fuel.
It's vast, but it's unstructured, and crucially, it doesn't usually tell you the actions the robot needs to take. Just shows the result.
Right. And the base of the pyramid.
Synthetic data. From simulators like Isaac Lab, this is potentially infinite in volume.
But maybe not perfectly realistic. Or historically hard to create.
Historically, yes. But the key principle here is to leverage all these layers. Find clever ways to combine the strengths of real, web, and synthetic data to get around that core data scarcity problem.
So general models first. Combine fast and slow control and use this pyramid of data sources. That's the research strategy.
That seems to be the core of their how.
Okay, let's focus on the Groot N1 model itself. The brain.
Right. Groot N1. They describe it as the world's first open humanoid foundation model.
Open. That's interesting.
Yeah, we'll come back to that. Architecturally, it takes in visual info from the robot's cameras.
What the robot sees.
And language instructions, like from a person.
Pick up the red block.
Exactly. And it outputs motor action tokens.
Motor actions, so the commands for the joints.
Yep, the specific, continuous values needed to control all the motors, make the robot move.
And how does it do that fast and slow thinking, the dual system thing?
It cleverly combines two different types of AI models. For the slower, System 2 part, understanding the language, reasoning about the scene, planning.
High-level stuff.
It uses a visual language model, a VLM. They specifically mention their Eagle 2 VLM. It handles the discrete information, the meaning.
Okay, VLM for understanding what to do, then what generates the actual movement.
For the fast reactive System 1 control generating those smooth, continuous motor commands, it uses diffusion models.
Diffusion, like for generating images.
Same underlying tech, yeah. But here, they've adapted it to generate these continuous motor actions and do it in parallel. This allows for that really fast high-frequency control, like 120 hertz, they mentioned.
So the VLM figures out the goal. The diffusion model generates the fluid motions to achieve it.
Wow, kind of like that, yeah. High-level goal meets low-level execution.
And how does this work if you have different robots, like different bodies, different hands?
That's the cross-embodiment support. It's trained on data from lots of different robots.
Single arm, two arms.
Yep, different grippers, different full humanoid bodies. The trick is it uses shared layers in the middle of the network that learn common patterns of movement, common representations that apply to all bodies, but then it has specific adapter layers at the input and output.
Tailored to each specific robot.
Exactly. So it learns the universal physics and control principles, but adapts them to the specific body it's currently controlling.
Neat. Like learning how to move generally, then applying it to your specific limbs.
Kind of, yeah. The core intelligence is shared. The interface is customized.
How big is this model?
They said it's a 2 billion parameter model, which is significant, but crucially, designed to be efficient enough to run on the edge compute, on Thor.
Right. Needs to fit on the robot. And performance.
They showed some benchmark results. Pretty significant gains over previous state-of-the-art methods.
Right.
Things like a 30% jump in success rate on certain manipulation tasks, getting up to 80–90% success on others. So real improvements.
And you mentioned it's open source.
Yes. That seems like a really key part of their strategy. They're putting the Groot N1 model itself, plus training data and evaluation protocols, up on GitHub.
Why do that? Give away the secret sauce.
They explicitly say it's to foster community collaboration, recognizing that embodied AI solving this robotics challenge is just too big for any one company. They want to build an ecosystem.
That is a big move. Putting a foundational model out there like that.
It really is.
Okay, let's circle back to data. Training a 2 billion parameter model needs a lot of data. We know robotics has this bottleneck.
Right.
How are they actually generating enough? This is where that simulation first idea really comes into play, huh?
Absolutely. Since you can't just download petabytes of real-world robot actions, their core bet is that high-quality synthetic data generated in simulation is the key to augmenting the limited real-world data they can get.
But wasn't creating good synthetic data always really hard?
Yeah.
Like needing artists, tons of manual setup?
Historically, yes. But this is where it gets really cool. They're using generative AI to generate the data.
Wait, using AI to make the training data for other AI?
Exactly. Using generative models to automatically create diverse 3D assets, randomize textures, lighting, materials in the virtual scenes, even generate the task goals and the reward functions for training.
So automating the creation of the virtual world and the training tasks within it.
Yeah. It drastically cuts down the human effort needed to create these massive, varied synthetic data sets.
That's leveraging their own strengths in a new way.
Totally. And they introduced this idea of digital cousins.
Digital cousins, not digital twins.
Right. Instead of trying to make perfect, photorealistic copies of specific real places' digital twins, they create simulated environments that are similar to the real world, but intentionally varied. Like cousins, not identical twins.
Why do that?
It lets them trade a bit of perfect fidelity for a massive increase in diversity and quantity of data. Focus on learning the general skills across many slightly different scenarios.
And they use a lot more sim data.
A lot more. In the Groot N1 paper, they said they used 100 times more synthetic data than real-world data.
100 times? Wow, so prioritize quantity and variety in sim.
For training those foundational skills, yeah. They also use techniques like trajectory multiplication.
Trajectory multiplication.
Yeah, using tools like dexmimogen, they can take just a few human demonstrations of a task.
Like someone teleoperating the robot.
Exactly. Maybe just 5 demos, takes 10 minutes to record. And then in simulation, they can automatically synthesize thousands of new, varied ways to do that task.
Oh.
By transforming the motions, applying them under slightly different starting conditions, different object positions, that kind of thing.
So amplifying the human input massively.
Hugely. They show this boosted the final policy's performance by 65%.
65% increase just from multiplying the demos in sim? That's a huge return.
It's a massive leverage effect. And then they take all these different data types.
The real teleop data, the synthetic data, maybe these multiplied trajectories.
Right, and they mix it all together in what they call the training soup.
Training soup. Okay.
Using clever data mixing and rebalancing techniques to make sure the model learns effectively from the massive synthetic data set, but still stays grounded by the real-world data.
And the sim data itself looks incredibly real in their demos.
The visual quality is getting amazing, which really helps close that sim-to-real gap, making what's learned in simulation more likely to work in reality.
Any other data sources?
They also talked about exploring neural simulations, using video generation models like Sora.
Generating video to train robots. How?
Well, the challenge is that generated video doesn't have action labels. You just see things happening.
Right. No joint angles.
So they're researching ways to learn latent action codes, kind of like a hidden language of actions that can be extracted from these videos and aligned across different robot bodies.
So potentially learning from actionless video by figuring out the implied actions.
That's the idea. Treating these neural trajectories as just another kind of embodiment data to throw into the training soup.
Man, they're attacking this data problem from every conceivable angle. Sim, multiplying real data, blending it all, even using generated video.
Seems like it. And crucially, this isn't just research locked away. They're pushing these techniques and tools into their products.
Into Isaac and Omniverse for developers.
Exactly, for the whole community to use.
Which leads us nicely into the workflows and tools developers actually get.
Right. They offer a whole suite of tools, mostly open source, built on Omniverse. Isaac Lab is key for the simulation and training.
Isaac Gyms within that.
Yeah, Isaac Gyms for the reinforcement, learning, training, and testing policies super fast. They also mentioned a tool called Cosmos.
Cosmos.
Yeah, it helps convert data and environments into photorealistic video. Again, helping bridge that sim-to-real gap visually.
Making the simulation look even more convincing.
Seems like it. And then specific workflows. There's Isaac Groot, which seems focused on generating those synthetic motions we talked about.
Okay.
And various mobility workflows. They split it, interestingly, relating back to the dual system idea.
Oh, yeah.
They have a remember workflow using VLMs and LLMs for that System 2 long-term memory and high-level planning.
The slow thinking part.
And then core mobility workflows for the fast System 1 navigation policies, plus a mobility gen pipeline just for creating the huge data sets needed to train those navigation skills.
Got it. And these work for different robots.
Yep. Their campus workflow apparently builds on imitation learning and then uses RL in Isaac Lab to fine-tune mobility policies for different embodiments, quadrupeds, humanoids.
And the big highlight there was...
Zero-shot sim-to-real transfer for mobility.
Wait, say that again? Zero-shot sim-to-real.
Yeah. Meaning a policy trained entirely in simulation.
No real-world data for that specific policy training.
Apparently. It worked correctly on the real robot straight out of the simulator.
That's huge. That's kind of the holy grail for sim-to-real, isn't it?
It's a massive milestone if it holds up consistently. Suggests the simulation fidelity and the training are getting good enough.
Wow. Okay. Any other key controllers?
They mention the neural whole body controller, codenamed Hover.
Hover.
This sounds like that low-level System 1 reactive controller, running at super high frequencies, hundreds, maybe thousands of hertz.
For balance and quick reactions.
Exactly. And they stress how crucial accelerated simulation is for training this.
How accelerated?
They give an example. Simulating a year's worth of robot experience in under an hour on one GPU.
A year in an hour?
Yeah, a 10,000x speed up. You need that kind of speed to iterate on something as complex as a whole body controller running at kilohertz frequencies.
That's just mind-blowing compute power being applied.
It really is transformative for how quickly you can develop these things. So yeah, these tools are meant to make the research principles usable for developers.
Okay, so we've got the motivation, the strategy, the AI brain, Groot N1, the data generation.
Yeah.
Now, the hardware brain that actually goes on the robot, Thor.
Right. Nvidia Thor, or Jetson Thor. The third computer in their strategy, they're pitching this as the ultimate edge compute platform purpose-built for humanoids.
Its main job.
To run those big, complex transformer models like Groot N1 efficiently and reliably right there on the robot.
The compute power actually walking around.
Exactly. They're calling it a supercomputer for humanoids.
Supercomputer. What are the specs like?
Up to 2 petaflops of FP4 performance.
2 petaflops? That sounds like a lot.
It's an enormous amount of compute, yeah. Specifically optimized for the kind of math AI models do, especially with low precision like FT4, lets those big models run fast on the robot.
Serious horsepower for an edge device.
Definitely. But it's not just raw compute. They also stressed sensor processing speed.
Humanoids have a ton of sensors, right?
Yeah.
Cameras, LiDAR.
Loads, generating huge amounts of data constantly. Thor needs to ingest all of that in real time.
So, high bandwidth.
Up to 425 gigabytes per second over Ethernet, which they said is a 10x improvement. Just massive bandwidth to get sensor data into the chip fast enough for the AI to react.
That makes sense. Need the data quick.
And they introduced something called the HoloScan sensor bridge to help manage that. Makes it easier to connect lots of different sensors over Ethernet with low latency.
Streamlining the sensor connections.
Yeah, and it has safety qualifications too, SIL2.
Safety is obviously huge for robots working near people. How else are they addressing that?
Multiple layers. On the chip itself, there's a functional safety island with isolated cores. The sensor bridge hitting SIL2 is significant. And they're working on AI-based safety too.
AI for safety.
Using onboard sensors, but also potentially communicating with external sensors in the environment, like in a factory, for an outside-in safety check.
So the robot knows about potential hazards even if its own sensors can't see them.
That's the idea. Multiple layers of awareness. Security is also layered.
How so?
Secure boot on the hardware, custom encryption for the AI models themselves, and using TPM's trusted platform modules for secure edge-to-cloud communication.
Got it. Layered safety, layered security. What's under the hood, chip-wise?
Based on their Blackwell GPU architecture. Has a transformer engine built in with native FP4, FP8 support.
Optimized for transformers like Groot.
Exactly. It also supports MIG, multi-instance GPU.
MIG, what's that do?
It lets you partition the GPU. So you could say, dedicate one part to running the fast real-time System 1 control, like balance, and dedicate another part to the slower System 2 reasoning and planning without them interfering with each other. Running different critical tasks reliably side by side.
Splitting the resources for different jobs. Makes sense.
Also has an enhanced CPU 14 ARM cores, much more general processing power, doubled memory to 128 GB, increased memory bandwidth. It all adds up to handle the complexity.
It really sounds like it was designed from the ground up for this kind of embodied AI task.
Very much so. And developers can get their hands on it soon.
Yeah, developer kits are expected June 2024. They're designed to make it easier to get started. Optimized layout for plugging in sensors, integrated storage, support for real-time OS.
So the hardware piece of the puzzle is falling into place quickly.
It really seems like it, which is fascinating, seeing all this capability emerge.
Yeah.
But it makes you wonder, what are the biggest hurdles still ahead? What's the ultimate goal here?
Well, they actually talked about the next bottleneck.
Oh, yeah. What is it?
Figuring out the scaling laws for robotics.
Scaling laws, like we have for LLMs.
Exactly. We know for LLMs, add more compute, add more data, performance goes up predictably. But how does that work for robots in the physical world?
Good question.
How does performance scale with more compute, but also with different types of data, real, sim, maybe that neural data? How do they combine?
We don't know those relationships yet for physical intelligence.
Apparently not. And they see the Groot N1 model as the key tool to start running those experiments to figure out those scaling laws for embodied AI.
Setting up the scientific foundation for scaling robots.
Kind of, yeah. And the ultimate vision. They talk about the ChatGPT moment for embodied AI.
What would that even look like?
They describe it as robots that can follow open-ended instructions. Any instruction, basically.
In any scenario. Home, factory, hospital.
Yep. Capable of doing pretty much anything a reasonable human could do physically. A truly general-purpose physical agent.
Wow. Ambitious.
Hugely. And they suggest the hardware, like Thor, is getting there or is on the path. The main limitation now is the AI building that truly general open-ended intelligence.
Which brings us back to that old idea, more of X paradox.
Right. The things easy for us humans walking, picking things up, are incredibly hard for robots. And the things hard for us complex math are easy for computers.
Yeah.
They frame robotics, achieving that general physical competence, as maybe the last grand challenge in AI.
After cracking language, vision, the physical world is the final frontier.
That's the perspective presented. And they're realistic, too. They acknowledge Groot N1 isn't the final answer architecturally.
Things will keep changing.
For sure. The field will evolve, maybe different AI approaches, better integration of vision and reasoning, figuring out that perfect interface between the big brain models and the fast, low-level controllers. That's still an open research question.
So lots to figure out.
And maybe the biggest challenge of all, safety and deployment.
Because these robots won't be in cages, they'll be working with us.
Exactly. They can move fast, they're powerful, but you can't just let them run full speed around people yet. Safety limits the speed.
Avoid the giant human nutcracker problem.
Huh. Yeah, that was a vivid phrase they used. Getting truly safe, compliant robots that can work closely and reliably alongside humans. That needs deep hardware and software co-design.
It's not just about capability, it's about trust and reliability.
Absolutely critical. And they circle back again to openness and community, saying this challenge is so massive, it needs that collaboration. Hence the open source group model and tools.
Makes sense. It's a multi-decade effort, probably.
Seems likely.
Wow. Okay, that was, yeah, an incredible deep dive into Nvidia's whole vision here. So much unpacked. From that staggering $1.4 trillion economic driver
Yeah, the numbers are wild.
to the three computer strategy, OVX, DGX, Thor, the really clever ways they're tackling the data problem with digital cousins and training soup.
Using AI to make the data.
Right. And the Groot N1 brain itself, mixing that fast and slow thinking with VLMs and diffusion models. And then the Thor hardware bringing supercomputing power right onto the robot.
It's a comprehensive picture.
So if we tie this back, thinking about Moravec's paradox, how the physical stuff easy for us is hard for machines, and robotics being maybe the last great AI challenge.
Yeah.
What does that actually tell us about intelligence itself? You know, how tied is our intelligence to our physical bodies, our interaction with the real world? Something to maybe chew on as you picture a future where these robots, powered by this tech, might actually be working right beside you.
A deep thought to end on. Makes you reconsider what intelligence really means.